Hello, and welcome back to the course. We're going to start looking at chapter 5, so section 5.1. We'll start looking at zeros of holomorphic functions. So, what is a zero? By zero, we just mean a point where the function is zero. So, zero of f is where it's the point where f is zero. That's what we mean by it. Now, by the identity term, zeros are isolated unless the function is constantly zero, right? Then it's zero everywhere. It's not isolated. Every point is zero. But if you have, a non-constant function, then the zeros cannot have limit points, right? So they all have to be isolated points. So in a neighborhood of a zero, at all the other points, the function is non-zero, right? In a small neighborhood. All right, so therefore, we have the following lemma, and we've used this, this idea of this lemma before, but we're gonna, parts of it. So we're gonna, prove sort of the more general version of this. So suppose that we have a zero at some point p. So f is a holomorphic function, and it has an isolated zero at p. So in particular, it's not going to be constant. It is an isolated zero. Then we can divide out by z minus p. We can actually divide by some power of z minus p. And so there's we're claiming that there exists a unique k such that we divide out. It's basically sort of the maximum k that we can, maximum number of times we can divide out by z minus p. So we keep dividing until what's left over, well, that's going to be holomorphic in the, wherever f is holomorphic, and that's going to be non-zero there, right? So we basically divide out. We get rid of the zero by dividing by the right power of z minus p. Right, and this k, this unique k, is actually it is the smallest integer, such that the kth derivative is non-zero. Right, so you could get at this k by looking at the derivatives of f. All right, so let's give a name to this k. Right, we're gonna call it the order of the zero at p. Although really it's sort of, if you say order, it's maybe that really talks more about the f rather than the zero. So it's the, f has order k, and it's when we're talking about derivatives, a lot of times, when people say order of something, it really means this idea about all the derivatives vanishing up to that. Right, so it's the first non-zero derivative. If the order is 1, we'll say it's a simple zero. We'll also, especially later on, we'll call it a multiplicity of the zero, and that's really what we want to think of as property of the zero rather than the property of f. Even though at this point that this distinction is more philosophic than anything else, but it's. We're going to call it a multiplicity of the zero. It's in some sense this, if the order is k, so if the multiplicity is k, really f has k zeros. They just all are at one point. That's the way that we're going to think about it. Because if you think about just, think in this formula, just g being 1. So f is z minus p to the k, right? Then it's a polynomial. And if we want to say that every polynomial of degree k has k roots, they just sometimes happen to be the same one. Well, that's exactly what that is, right? So that's why we call it a multiplicity, right? So, and that's really, we're saying it's the multiplicity of the zero, and really the order is sort of referring to f, right? Okay. So an equivalent definition of the order, as we'll see, is that, or you can easily show once you have this lemma is that is the largest k such that if you divide out, you get something bounded near p, right? Which is, well, I mean, if this g exists, it's it's bound. That's what g is, right? That's what the thing is, clearly bounded if it's going to be holomorphic, right? So that could be another version of what we mean by order. If you divide out by z minus p, you get something bounded. But the lemma says something stronger, right? Now, another way of giving the order, and by the way, all these things are about holomorphic functions. Some of these terms can refer to real functions, but the results are much more complicated for just real differentiable functions. But for holomorphic functions, it's basically if you have an f with 0 of order k, then you can also write this in some neighborhood, in some disk, maybe small disk, but in some neighborhood of p, you can bound f from both above and below by, well, really the z minus p to the k. Well, let's put absolute values in there, right? And you have to put some constants in here, right? But basically, it behaves like z minus p to the k in absolute value as long as you put in some constant. So it's how fast it goes to 0. It doesn't go any faster, any slower than z minus p to the k. All right, now the conclusion of the lemma that you can divide out still holds if k is 0, right? For trivial reason. I mean, so then you're dividing by z minus p to the 0, right? It's just you're dividing by 1, right? It clearly holds, right? So you could say that the order is then 0, and g, the quotient. I mean, it's just f, right? F divided by 1 is f. So you could still say that this holds for trivial reason when k is 0, sorry. So you could say that if f is not actually 0 at p, then it has a 0 of order 0. You could say that. And it's sort of, in some settings, it makes, it might be convenient to think in that way. And we'll even see negative orders in a little bit. Those are going to be the poles. But really, if we say f has a 0, right, we're going to mean an honest 0, an actual 0. F is 0, right? Because if we always had to specify, well, it's 0 of positive order, well, that would be inconvenient, right? So we'll, if you want to use this sort of, trick of language, then make sure to say that it has a 0 of order 0, right, or something like that, right? But otherwise, if you just say f has a 0 at p, everybody's going to take it as f of p is 0, right? So we're gonna stick with that. All right. Now, if all the derivatives are 0 for all k at p, then we could say that f has a 0 of infinite order, right? But as we've just, as the lemma says, right, once you prove it, it's, basically once we have an isolated 0, it's of finite order, right? So for holomorphic functions, infinite order 0, well, it just really means that the power series is 0, and it's the function is just identically 0, right? So for holomorphic functions, infinite order 0 just means the function is identically 0, right? So right, so every 0 non-constant holomorphic function has finite order. I just said that. Right. Now, it is not true if you just take real differentiable functions. Let's just take real differentiable functions on R, and let's even take an infinitely differentiable function, right? So if you take an infinitely differentiable function such as, this guy, you can prove that if you let f be 0 at 0 and be given by, the exponential of minus 1 over x squared, that will be infinitely differentiable, right? You have to define it piecewise, but otherwise it is infinitely differentiable function. It's a really nice function, smooth, nothing wrong with it. But all the derivatives at 0 are 0. Every derivative at 0 is going to be 0 of this. So if you look at the Taylor series of this is just an identically zero Taylor series, right? This is actually an example in basic real analysis of a function that is not real analytic function that doesn't convert whose Taylor series doesn't converge to the function. The Taylor series here is just the zero Taylor series, and it converges to 0. But the function is non-zero except at the origin. The origin is the only place where it's 0, right? So it does have an isolated 0 on R. It's the only place where this 0 is at 0. But it's a 0 of infinite order, right? For this f. But for holomorphic functions, this doesn't happen. This is not a holomorphic function. So you cannot make this into a holomorphic function at 0, right? So there's no way to extend it to make it a holomorphic function, for example. So for holomorphic functions, all zeros are finite order. They're all kind of nice. All right, so let's prove the lemma. So we have an f defined on U, right, and it's 0 at P, right? So if we divide, if we look at this function, the quotient, right? So we divide by z minus p to the k. Now for any k, this is going to be holomorphic on u minus p, because 1 over z minus p to the k is holomorphic everywhere except p, right? So this is definitely holomorphic everywhere except p, right? So that's true for any k, right? So we just need to figure out, the point is what happens at p, right? Now, so in some disk around p, so we look at the power series, right? So power series of f. Now, it's f is 0 at p. So c 0, the first guy, the constant term, that has to be 0, right? Because it is 0 there, right? All the other terms in the power series are 0 when I plug in z equals p. So it really starts, the power series really starts at some k, right? It's 0, and then at some power it starts, right? It's basically, we look at the smallest Cn, where Cn is non-zero, right? That's actually gonna be Rk, right? Because all those Cn's are given by, the Cn is given by the nth derivative, right? You have to put in divide by the n factorial, but otherwise it's just the nth derivative, right? So if so that's the furthermore in the lemma, right? So we look at the first derivative, right? That's non-zero, and we start the power series there, right? Now, once we have this thing, we can write down this, right? We just divide out by z minus p. We divide out each term, right? So each term is divisible by z minus p to the k, right? So we just divide it out. We get another series, another power series over here. That power series converges in this disk because the original power series converges into the disk, and we just we just divide it out by something, every term by this, for any particular z, when we're looking at this convergence, we're just dividing by a constant, right? Once z is fixed, right? So it doesn't change convergence, right? The convergence of this second power series is the same as the convergence of the same first power series, right? And as I said, the k is the smallest, and so that Cn is non-zero, right? So that gives you the furthermore, right? And this is giving us the G near P. And K is clearly bigger than 0 because F was actually had a 0 there, right? It had an isolated 0, right? So C0 had to have been 0. Okay. Now, this series, like we have already a definition of G outside of P, and now we have another thing that's going to give us the G, right? Well, we'd better get that those things are equal, right? Well, outside of the origin in this disk where the series is defined, well, how did we get it? It is precisely the thing, where we divide out by z minus p to the k, right? So if f is equal to this series, then f over z minus p to the k is equal to this series. So on this disk, we get that series is, or well, in the punctured disk at least, we get that series is equal to G, because so far we've only defined this G in U minus P, right? But we can now define this G at P, right? We just set G at P is equal to CK, right? And with that definition, G is actually equal to this power series in this entire disk, including at P, right? Because that's what you get when you plug in Z equals P. You get precisely CK out of that series. So if we let G be that, at that point we get precisely this function. Now we have this G is holomorphic everywhere outside of P. At P we just defined it, right? But at P it is also holomorphic because it's analytic, right? It's given as a power series at P, right? So now we have that it is a holomorphic function in U, in all of U, right? Okay, so now let's prove that the K is unique. So suppose that we have, two different G and two different Ks, right? We have this guy, one version of F, and this guy is the other version of F. And let's suppose that G1 at P is non-zero and G2 at P is also non-zero. So these are, those would be the two different G that would maybe come out of this lemma for two different K, right? Let's see that that actually are the same thing. So suppose, without loss of generality, that K1 is less than K2, so that we can write down this thing. We can basically just move, we divide by z minus p to the k1, right? And we write down this equality, right? And we just plug in z equals p, right? And that gives us, right, because these guys are non-zero, right? That gives us that k2 is just k1. All right. All right. So now another useful lemma about zeros of order k. Now, near a zero of order k, if you just look locally, claim that a holomorphic function really just acts like z to the k or z minus p to the k, right? We saw a little bit of that before, but it really, it acts in a very strong way, like z to the k or z minus p to the k, right? We can always take the p to 0. That's why I'm saying z to the k, right? So it's really in a very strong way. We can actually change variables in a holomorphic way, in a biholomorphic way nearby, and just make the function z to the k, right? So that's the point of this next theorem. If I have a holomorphic function and it has a 0 of order k at p, right? So it's an honest 0, right? I'm saying that k is in n, so k is a positive integer. Then there exists a function g. It's going to be different g than in the last lemma, but there exists a function g which is the kth root, right? So we have this function g holomorphic in a neighborhood. Now this neighborhood might be smaller than this whole thing. We won't necessarily be able to do it in all of U here, but definitely in some small neighborhood, we're actually just going to make it a disk. So there is some neighborhood of P where we have a kth root, right? So we have a holomorphic function G whose kth power is F, and furthermore, G is 0 at P, right? Well, I mean, should be. it's F has 0, but also G prime at P is not 0, right? So G has non-zero derivative. That's the biholomorphic change of coordinates. So this is the fancy way of stating this is that there exists a local biholomorphic change of coordinates that takes P to the origin and makes F into Z to the K, right? That's basically what this says, right? All right, so let's prove this. So again, as I said, we're going to make V be a disk. So let it be a disk such that, well, F has an order of 0 of order K, that 0 is isolated, so I can choose a small enough disk where F is only 0 at P, right? So it's non-zero in the puncture disk. So the lemma says, the lemma that we just proved, right, says that there is a holomorphic H, so we're going to call it H now because that was G before, but now it's H. G is now something different. So a holomorphic H such that which is non-zero at P, right? It's the quotient, and basically we divide out by the kth power of Z minus P. So we divide out all the zeros. That's what we're doing, right? Now, H is not 0 at P, right? Therefore, it's not 0 in the entire disk, right? In entire V, in this guy, because F was non-zero there, and the only way for H to be 0, right, would be for F to be 0, right? So outside of P, right? So that means that that H is non-zero in this entire disk. It's nowhere 0, right? And so since the disk is simply connected, we've proved before that means that there is a kth root. In a simply connected domain, if we have a nowhere 0 function, then it has a kth root for any k, right? So that means that we can find a kth root of this H. We're going to call it phi, right? At least in this V, right? It's not going to, again, it's not going to work for the entire U, but in some small neighborhood, it does, right? So for the H, we can find a kth root because it has no more zeros, right? And what we divided out, Z minus P to the K, that has an obvious kth root, right? Z minus P, right? So we let our G be Z minus P times the kth root of H, which exists because H was nowhere 0 and the disk was simply connected, right? So therefore, we get these two things, right? We get that F is G to the K, and we automatically get that that this G is 0 at P, right? We've added that 0 in there, right? And now we also get that the derivative is non-zero just by computing the derivative here, right? So you compute the derivative, you get you use the you use the product rule, right? And so the derivative of g is z minus p times the derivative of phi plus phi, right? Now, if I plug in p, right, this first bit just goes away. So really, I have g prime at p is just phi at p, right? Now, phi at p is not zero because h is not zero at anywhere here. So its case root is not zero, right? Obviously. So therefore, g prime at p is non-zero either. Now, one last note here is that every semester there's someone on the homework that uses L'Hopital's rule. And L'Hopital's rule still works for holomorphic functions. I mean, it's a it takes a little bit of work, but it still works for holomorphic functions, even though now we have functions in the plane, not just on the real line, but it still works. And really, the proof for holomorphic functions is actually easier. You just do this, do these divisions, right? So now, actually, with the lemma that we have, you can actually prove L'Hopital's rule, right? So now, and it's fairly easy now, right? With that lemma, it's fairly easy to prove L'Hopital's rule, right? But it does take a little work, right? I mean, we are talking about, you cannot just use the L'Hopital's rule from just basic real analysis, because that was just, for a function defined on the real line, and these limits were just on the real line, and those derivatives were not the holomorphic derivatives. I mean, on the real line, if you had holomorphic functions on the real line, they would be the same derivatives, but the limits that you're taking are then not really the same. So it's not the same thing, but we get the same sort of result, right? So if you have two holomorphic functions near P, and they have an isolated zero, then you can this limit exists. The limit of the derivatives exists. That's the limit of the quotient of f and g, right? And it's basically by dividing out all the zeros is the way to look at it. Although a lot of times you can just do that instead of computing the derivatives. So it's it's sort of it's simpler in the holomorphic setting. So anyway. So that's it for this time. And so next time we're going to look at singularities, so isolated singularities. So, now we're looking at, when the function is 0. So next time we're going to start looking at when the function actually is not defined there, and what sort of, how bad it is if it's only not defined and not holomorphic at a single point, right? So we're going to look at the types of singularities, and we're going to prove the Riemann extension theorem, which is sort of one of the fundamental terms about holomorphic functions, which is a little amazing. And even though it's just sort of seems like a simple theorem, but definitely not something that's true about real differentiable functions. This is something that's very special to holomorphic functions. It says that if the function is not defined at a single point, but it's bounded nearby, then it's actually, it extends holomorphically. It's actually just a holomorphic function that you are just not looking at a single point of it, right? You restrict it to a punctured neighborhood, basically. Right. It says that, all the singularities that are actually singularities, you have to blow up in some way. Right, that's only true for holomorphic functions. So nothing like a step function kind of thing, or anything like that. for holomorphic functions, right? So all right, so that's next time. So see you then.